we're now going to move on to talking about geometry of the molecules and what their physical shape looks like, because that's what we really need to do to find the polarity of these molecules. Okay, geometry. So this is something else you should remember from before. We know that in a particular molecule, the electrons want to be really spread out because they're all the same charge, they're all negatively charged, and they don't want to be close together. So the electrons want to be as spread out as possible around the central atom or several central atoms. So there are two types of electrons in a molecule. They're all the same electron, but they're in two different kinds of positions. There are lone pair electrons, and there are bonding electrons. We call those lone pairs and bonding pairs. And we saw those in our picture that we did on the last group. Here's an example. If we have an HCl molecule like this, the electrons here that are in between the hydrogen and the chlorine holding them together, those are the bonding pairs. And the lone pairs that are on the end that only belong to one atom, those are the lone pairs. So pairs of electrons have another name. They're also called electron groups. One electron group is the same as an electron pair. Okay, so now we have to look at the two types of geometries. Both of these are geometries that you need to find, but one of them is more important than the other one. So the first geometry that you find for your molecule is called the electron group geometry. And in this kind of geometry, all electron groups are considered equally. So it considers lone pairs and bonding pairs. So we find that one first. We count all of the different electron groups, and once we've finished our count, then we go back and we count again. And this time we count for the molecular geometry. And in the molecular geometry, this describes the physical shape of the molecules. And because lone pairs don't add any information about the physical shape, this type of geometry only considers the bonding pairs. Only the bonding pairs. So this second one, this molecular geometry, this is the one that you want to report. When someone says to you, what is the geometry of this structure? They're talking about this one. So I'm not going to go over all of it, but I will mention that in the worksheet that I posted for you, there is a 2-page table taken out of a textbook that I particularly like, and this includes one column for the electron, number of electron groups, and within a particular electron group, another column for the molecular geometry, the number of molecular groups. As you slowly take away, if 0 of them are lone pairs, if 1 of them is a lone pair, and if 2 of them is a lone pair, and gives you all of the names of the different kinds of structures and shapes. And there are 2 pages all the way up to 6 electron groups. So I'd encourage you to use this if this is a little far back reaching for you. Okay, so let's go back and do the geometry for the examples we had on the last page. So here we've got NCCN, and there are 2 central atoms, the 2 carbons, and we can label the geometry for each of them, but they're in the same situation, so we'll just do it once. So electron geometry includes both the lone pairs and the bonding pairs connected to that central atom. So this central atom, carbon, has 1, 2 pairs of electrons touching it. So there are 2 electron groups. And something with 2 electron groups is called a linear structure. So now for molecular geometry, we eliminate any of the electron groups that were lone pairs. And as we can see here, neither of these were lone pairs. So there are 2 bonding groups, still have the same number. So our molecular structure for this molecule is linear. And so that tells us about the shape of the molecule and what it's going to look like. And again, this is true for both of the central carbon atoms in that molecule. Okay, let's do the next one. So nitrogen is the central atom here, and nitrogen has 4 electron groups attached for those 4 hydrogens. So there's 4 electron groups, and we call a molecule with 4 electron groups tetrahedral. This is going to be a favorite in organic chemistry. So now we go back from molecular geometry and we recheck our count and we eliminate any of them that are lone pairs, and none of them were lone pairs here. So we still have 4 bonding groups. And so our molecular geometry is also tetrahedral. Okay, you could better do one where they're not the same, or you're not going to believe me that you have to do both of these. So let's look at our final structure. So in this case, there are 2 central atoms. There's this carbon, and there's this oxygen that's attached to the hydrogen. Those are 2 central atoms, so we can look at the electron geometry for each of those. So let's look at the carbon first. Okay, so the carbon is attached to 1, 2, 3 electron groups. And I know what you're saying to yourself, Rachel, this is a double bond, there are 4 electrons there, but this is considered 1 electron group. It is 1 item, 1 atom that carbon is attached to, so it just counts as 1 group. That's 3 electron groups, and if you have 3 groups attached to you, you are called trigonal planar. Should all be coming back to you now. If we redo our count for the molecular geometry, we can see that all of those are bonding electrons. So we've got 3 bonding groups. So that molecular geometry is also trigonal planar. I'm going to abbreviate because I'm running out of space here. Trigonal planar. And that's just for this carbon. And then we'll do the geometry for the oxygen that's attached to the hydrogen. Okay, electron groups. So we've got the carbon is the first group, the hydrogen bond is the second group, and then each of these lone pairs is an electron group. So there are 4 electron groups here. And something with 4 electron groups is called tetrahedral, just like above. And now for molecular geometry, we finally have a couple of lone pairs. So in molecular geometry, lone pairs don't count. We only count the actual bonding electrons that are attached. So there are 2 pairs of bonding electrons. So there are 2 bonding groups. And this is where you can use the table if it's not coming back super quickly. So we would find 4 electron groups in the table, which is called tetrahedral. And then we would go to the third column and find 2 lone pairs. And 2 lone pairs is called bent, just like for a water molecule. So 4 electron groups with only 2 bonding groups, that is called bent. Again, if this isn't looking familiar to you, have a look back at the chapter on Lewis structures and give yourself a quick refresher on how this works. Okay, our last topic is polarity. And polarity is particularly important when we're talking about liquids and solids, because liquid and solids have much more significant intermolecular forces between molecules. So we need to know about the polarity of each molecule to know how they're going to interact. So when we have a molecule with a series of atoms in it, the atoms are connected by bonds. And the bonds do not always share electrons equally. In some parts of chemistry, we like to pretend that these bonds equally share electrons between both sides, but in this case, in reality, the electrons are not shared equally. The more electronegative side has more of the electrons. So let's go back to our hydrogen chloride example here. So we know from our previous chemistry experience that chlorine is very electronegative. It's very close to the top right corner of the periodic table, and hydrogen is not very electronegative. So this one is going to be more electronegative. And hydrogen is going to be less electronegative. I'll abbreviate. And so what we do when we label the polarity is we use an arrow to point towards the side that is the most electronegative. So if I were going to point towards the side that were the more electronegative, I would point this way towards chlorine. So my arrow would look like this, pointing towards the chlorine side. And just to indicate that this side is the negative side and this side is the positive side, we put a little tail on the left side so that it looks more like a plus sign. So the hydrogen side is more electropositive, the chlorine side is more electronegative. We can also use these lowercase deltas to indicate a partial positive charge on this side and a partial negative charge on this side. And so we call this a dipole moment, meaning that the electronegativity of the two atoms in this bond are not the same. And so what we can do is we can draw one of these dipole moment arrows for every bond in our entire molecule. And we're going to sum them together. So the sum of all the dipole moments in the entire molecule is the one that we care about. We'll call this the net dipole, or the net dipole moment. And so we need to ask ourselves, does our molecule have a net dipole? So if the molecule has a net dipole, it's present, then this is going to be a polar molecule. And if there's no dipole present, no net dipole, I should say. If there's no net dipole present, the molecule is going to be nonpolar. And remember, it's not that there are no dipoles. There could be dipole arrows between some of the bonds in the molecule. What we care about is the sum. So if the sum of all of the dipole moments cancel each of them out and have a net dipole of 0, the molecule will be nonpolar. So let's go back to our examples on the previous page and add that in. Let's see, we're doing blue now. Okay, so here's our first molecule, and we said it was linear. So this is an accurate representation of what it's going to look like in real life. So if we were to draw in a dipole for each bond, this bond in the middle between carbons doesn't have a dipole because these are the same atom on each end. If we compare carbon and nitrogen, nitrogen is the more electronegative of the two. So our atom would point towards a nitrogen, and on this side it would point towards a nitrogen. So do we have dipoles? Yes, we have two small dipoles, but they point in opposite directions. So if we were to add these two together, we would find that there is no net dipole. in this molecule. Okay, let's look at our second one. So this is our picture of the structure in a 2D fashion, and we said that it was tetrahedral, so we can do a better job drawing that picture here before we label the dipole. So let's try and draw it more like a tetrahedral structure. Kind of like one hydrogen on top and a cone, a triangular prism on the bottom. Okay, so for each of these bonds, nitrogen is more electronegative than hydrogen. So if we were to draw in each of the small dipole moments, they would all be pointing towards the nitrogen. And it can be difficult to tell from the structure, but if you were to add all of these small dipoles together, you would find that there was no net dipole again in this one. All of those small dipole arrows cancel out. All right, now for our tricky one here at the end. So there are a lot of bonds in this molecule, but we're just going to focus on the ones that are the most significant difference in electronegativity. Oxygen is one of the most electronegative atoms that exists. And so if we were to draw a big arrow for the net dipole moment in this molecule, it would point towards the side of the molecule with the oxygen in it. So there would be a small arrow pointing from carbon to oxygen in this bond, and a small arrow pointing from carbon to oxygen in this bond. So the net dipole would be pointing in this direction, as sort of an average of the two. So the dipole does exist for this one. Okay, so that should be enough information that if you're presented with a molecule, you can draw the Lewis structure, determine its physical geometry, and identify if it's a polar or a non-polar molecule.